Okay, so today we will complete the couple cluster theory. So last class we wrote the we wrote the Hamiltonian in normal order. So that was the main thing we did. So we took the second quantized form of the Hamiltonian, then we rewrote the strings of operators involved in it as normal ordered plus contracted terms, and we obtained an expression for the normal ordered Hamiltonian, which is this last line here, that the normal ordered Hamiltonian is basically the original Hamiltonian minus the expectation value of the Hamiltonian with respect to the vacuum, or the reference function which has been used for normal ordering it. So we will start there today. So this is what we arrived at, and this is of course just a number which I can write as E0. So if you remember the operator equation for Hartree-Fock, for couple cluster, it looked like this. Right? So basically and I told you that to obtain the energy expression as well as the expressions for determining the cluster amplitudes, which are my variables, I have to project this equation with either the ground state function, so with phi Hartree-Fock, or with the excited functions. And this we can call H bar. Okay, where this is the full Hamiltonian. But if I write the Hamiltonian in normal ordering, okay, which is something that will simplify my algebraic manipulations and also evaluation of terms later. We will see that today. So then we can write H as Hn plus this number. So I will end up with e to the power minus t Hn Hartree-Fock, and I can write this as which is basically my correlation energy. E0 being the Hartree-Fock energy. So now my task is reduced to, well, you don't know if it's reduced, but what you need to evaluate now is the similarity transform of the normal ordered Hamiltonian. Okay. And of course, since the Baker-Campbell-Hausdorff is an algebraic relation, that is applicable to the normal ordered Hamiltonian as well. So we now have to evaluate. So let me call this H bar instead. Okay. So then H bar is equal to Hn plus Hn commutator plus Hn commutator T, etc. Okay. And Hn also contains at most 4 operators. So this also terminates at the quartic power of T. So I think that is Hnt, 1T, 2, 3T, 4T. That is the last term in this expansion as well. So our task is now to evaluate every commutator. So we just have to keep doing that systematically. So Hn also has a one body part which we can call Fn, and it has a two body part which we call Vn. Okay. Now, and my T, let's say I approximate to T1 plus T2. So this is the CCSD approximation. And then we will only do one term in class, but you can work out the rest. So let's do one term, which is FNT1, the simplest one. So that is equal to FNT1 minus T1FN. And if you remember what T1 looked like, it had an amplitude. So this is called either a T amplitude, a cluster amplitude, or what else is it called? Is it called something else? Or an excitation amplitude, yeah, it is called. It can be called three different things. They're all the same. AA dagger, AI. So that is the T operator. And Fn is basically some PQ. FPQ. So what is FPQ? FPQ basically is the HPQ. Right. So it's the expectation value of the small h operator. AP dagger AQ. So I'm writing it as FPQ for an analogy with the Hartree-Fock operator. So this may be called the Fock part of the Hamiltonian in a way. So you could include some effective part of the some part of the two-body term into this one-body term as well. So the part that goes into the Hartree-Fock operator. But you could also keep it at the truly one electron integral level. So then you would call it HPQ. So in the notes by Crawford, they have written it as FPQ. So I am writing it there, but writing it as FPQ also. But you can do the couple cluster theory just with small h as well. Okay. So FPQ is this. Sorry, the normal ordered part of the Fock operator is this. So what is the difference between the normal ordered Fock operator and the normal one? That is just the operator over here. So this has a different order for the occupied orbitals and the unoccupied orbitals. Remember, this is a normal order with respect to the Hartree-Fock function, the Fermi vacuum. So depending on P and Q, this curly brace will either keep the string unchanged or it will swap it. Okay, and we will gain a negative sign if we swap it. So in which case is it swapped? When it is an occupied orbital, then the operator order will be swapped for the occupied labels. But for the unoccupied labels, you will still retain the dagger before the undaggered operator. So that is all the difference here. So now let's just continue with the algebra. So we will do FNT1. This is what we need to evaluate. So here you see we have ended up with a product of normal ordered operators. So how do we evaluate that? So one way would of course be to actually carry out the operation of normal ordering, open them out And then after that, apply the original Wix theorem to again rewrite them in terms of normal ordered string. But that is a lot of work. Instead of that, there is a algebraic simplification. So there is something called the Generalized Wix Theorem, which tells you what to do with products of normal ordered operators. So what is this Generalized Wix Theorem? It tells you that if you have a set of or two strings of normal ordered operators, then you can write them as a joined normal ordered string plus contractions which are only between the strings. So like this. Plus all the similar terms, and then also things with two contractions. Etc. So if you think about it a little, it's quite an intuitive theorem, because once you've normal ordered a string of operators, you've already excluded the contractions that are possible among the orbitals that are inside the bracket. So those are already excluded from this normal ordered term. So when you multiply two such strings, then the only other contractions that you now need to take out from this are the ones which are where one operator is from the first string and the other one is from the second string. So it is kind of intuitive. Of course, you can prove it in a general way from the original Wix theorem. So this is a derived theorem in a way. But I don't need to do that in this class, but we will make good use of this. So this is actually the more useful form of Wix theorem and also what is more commonly used. And it also gives you fewer terms than the original Wix theorem. So in that sense, this is what you will keep using. So when I'm evaluating Fn T1, I only need to contract things between the strings. So like this, okay? Only the terms which come, one from the first string and one from the second string. So let's see what that is. FNT1, some PQ, some IA, FPQ, TIA. And let me put a bracket here. P dagger, AQ, AA dagger, AI. So this is the joined normal ordered string. And then we will have the contractions. So here, now, remember again that this is normal ordered with respect to the Fermi vacuum. So, in order to determine which is a non-zero contraction, I need to look at the labels of the operators. So, if I want to contract something with AA dagger, okay, the only non-zero one is when I have a annihilation of the A on the left of AA dagger. So this is a non-zero contraction, one of them. Okay. Then let's see if there are others. So now to contract with I can again I need a dagger because this is an occupied one. So this is another non-zero contraction. So now let's look at the double contraction. So two contractions. That is now basically the same two contractions. And then I have so this is multiplied with this. Okay, I hope you're not confused. Plus, okay, so this is delta QA. And I have AP dagger AI. Then I have delta PI, AQ AA dagger, plus delta PI, delta Q A. Okay. So now I can, of course, simplify my delta functions as I like and get the final expression. Okay. You can do that yourself, no problem. Then I need the second term from the commutator, which is T1Fn. And what is the operator that it has? This is AA dagger AI, and then AP dagger AQ. This is equal to AA dagger AI, AP dagger AQ, plus, again, contractions between strings. So let's see which one can exist. So I have a AA dagger. So the only non-zero contraction possible with an AA dagger if there is a annihilation operator on its left. So that is not here. So AA dagger cannot be contracted. For AI, the only non-zero contraction is when you have a dagger on the left, which can take a label of I. So that is also not there. So here we don't have any contracted terms with T1N. Now, what is the commutator value then? So FNT1 minus T1FN. So let's look at the two uncontracted strings. So are they the same or are they different? So let's see. So if I want to rewrite this one as the first string, what do I need to do? I need to exchange, I need to take P 2 steps and then Q 2 steps, right? So that's 4 interchanges. That's minus 1 to the power 4 of AP dagger, AQ, AA dagger, AI. So they're basically the same string. So when I take a difference, the uncontracted string will cancel. And I will only be left with the contracted terms from the first expression here. So that is sum PQ, sum IA, FPQ, TIA. Delta QA, APAI, plus delta PI, AQ, AA dagger, plus delta Pi delta QA. Okay. Now so there is lots to learn now from this expression. So firstly, the uncontracted strings, they always get cancelled when you have a commutator, because if you have if you have an AB string and you want to convert it to a BA string, and both A and B have even number of operators, as in the case of H and T, then you will always need a even number of permutations to write one string in terms of the other, which means that the uncontracted normal ordered strings from AB and BA will always be the same, and when you take a commutator AB minus BA, they will cancel. Okay, that's the first thing that we learn, that uncontracted string is cancelled. What is the next thing that we learn? The next thing that we learn is that when you are going to project with a function, what will happen? So if we project, or if we take expectation values with respect to the Hartree-Fock function, which is what we will have to do for the energy expression, then only the fully contracted term will survive. We have seen this before as well, but now we have an actual expression for the contribution of this term to the energy expression. So if for expectation values such as the energy expression, only the fully contracted term will survive. This we've seen before. But now we also know what we will get when we project with an excited function or an excited determinant. So on projecting with chi, remember we called the excited determinants chi, then what will survive? That is also obvious from here. So then let's see, this is double tick. So then the terms which have some operators, those are the ones which will potentially survive. Of course, depending on which excited determinant you project with, a subset of these terms will survive, because it depends on the actual index of the term that you're of the function that you're projecting. Okay, because say if you have a singly excited determinant which is projected on this commutator, then you can write it as the action of a de-excitation operator on this bra, and then this de-excitation operator, this is also a normal ordered operator, you will take a product of this normal ordered string with these two, let's say this string, and again from these two strings you will have to construct only the fully contracted term. Okay, so this sounds a bit vague to you now, I'm sure, so but hopefully I'll be able to show you one. So let's do one of them then.
Madam?
Yeah?
Before that, can you go to the FNT1 term? I could not pay concentration on that point.
FNT1 term?
Yeah, anyone will be fine, T1 FN or FNT1.
Yeah.
So you, while you evaluated the T1 FN, you did not consider the contraction of the next term. So why is that?
Oh, because here no non-zero contractions are possible. So if you want to contract something with AI, for example, then the only non-zero contraction is if you have some AI dagger AI form, or okay, so that is not possible. There is no daggered operator to the left of AI.
So for the contraction, there should be a dagger operator in the left and the undaggered operator on the right.
On the right, if the orbital label is an occupied orbital.
Okay, so a dagger with AQ cannot be contracted in this case also.
No, because for the unoccupied orbital, it is the reverse. You
Okay.
need a annihilation operator on the left and creation on the right.
Okay, notes. Okay.
Yeah. So this is the okay. So let's do something. So now we have this commutator FNT1. So we have evaluated that. I won't write it again. Okay, I'll just show you this one. This is equal to commutator FNT1. Okay. And I now want to project with some j to b function. So how can I write chi j to b? That is equal to phi Hartree Fock, and you will have AB AJ dagger. Okay, because this is the adjoint of chi j to b, that is AB dagger. So this is the adjoint, and now I am evaluating. Okay, so the term that the total term is this, and a part of it is this FNT1 commutator. This is only a part of it. And so this is phi Hartree Fock, AB AJ dagger. And okay, I should write the normal ordering as well. And here, from the commutator expression, I have AP dagger AI operator and AQ AA dagger. So the fully contracted term, let me write that first, because and you have all the amplitudes as well. Some PQ, F, PQ, TIA. Yeah, so here what happens, you see that you have an expectation value and you have an excitation operator in the middle. So this is certainly 0, because AJ dagger acting on phi Hartree Fock will annihilate phi Hartree Fock, because you cannot create in a occupied orbital. So this is 0. So the terms which can remain are the things are a bit long to write. So if I'm pressed for time, it becomes a bit difficult. Okay, so AB AJ dagger. Okay, so we have delta QA AP dagger AI. Phi Hartree Fock. So now again we have to contract between the two strings, and we have to get the fully contracted term, because then it's an expectation value that we have to evaluate. So the AJ dagger can contract with AI because they're both occupied. And then AB can contract with AP dagger because P is a general index. So this is one term. And then similarly, you have the other term. Okay, I'm not writing it just to save time. Okay. So then I have some PQ, FPQ, TIA, phi Hartree-Fock. So what do I have now? I have delta BP, delta JI, delta QA, phi Hartree-Fock. This is one term, and you have another one coming from the other component. So phi Hartree-Fock, that is the normalized, so that's one. So now all I need to evaluate is this. PQIA. So this is equal to, so my P will become B, Q will become A, then I will become J, and A will be A. And what is the only sum that is remaining? That is A. Okay. So we simplified our expression to a single term, and here, and there will be one more term here. Okay. So you can take that as homework to do the evaluate the second term using this. So let me write this. So this is B, let's say, and I will put B, 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 so that you don't forget that there is a second term. Okay. So what have we reduced? Our matrix element of chi with a matrix element between chi and phi 2, we have simply reduced it to a matrix multiplication with one contracted index. Okay. So this is simple matrix multiplication. So eventually all the terms, whether it is FNT1 commutator or FNT2 or VNT1, VNT2, or even the nested commutators, all of them are reduced to sequences of matrix or tensor contractions. If you want me to be general, but they're all reduced to a sequence of tensor contractions. So if you had, so I'll give you another example. So if you had a V T1, T2 term, let's say. So this is not just a multiplication. I'm saying something that involves V, T1 and T2. So something like this, then one of the terms there could very well turn out to be, IJKL, T, I to A, T, J to B, K to C maybe, and it is contracted then over IJ, IJ and K. So it's contracted over IJ and K. So this term would contribute to the terms where the projection is by chi, so the remaining indices, that is L to C. So I can write this sort of in reverse order to make it look a bit more like matrix multiplication. So this is the convention how you write it. It doesn't matter. So what is contract? So the matrix multiplication is over ij, and no, this looks a bit bad. So let me write it as C, and then I can contract over C. So I'm just writing this randomly. That is why I had to adjust a little bit. So, okay. So IJC, IJC. So there are 3 contracted indices, and I am left with then chi, let's say L to A and K to B. And okay. And whenever you're projecting with an excited determinant, that is the equation for the corresponding t variable. So TLK to AB. Does that seem reasonable to you? So we say that this is the equation for a particular cluster amplitude, because how to put it simply. Okay, I guess unless I tell you that tell you the iterative scheme, it doesn't make sense to you. So basically, so I have this big equation, and I need to evaluate all the terms in this equation. And I have shown you one example of one particular commutator, and you can similarly do all the rest. Okay. Then the 2 things that you need to do is find the expectation value of h bar with respect to phi Hartree-Fock. That is your energy expression. And you need to find a set of coupled nonlinear equations which will tell you what the values of the cluster amplitudes are. And to get these equations, you will project turn by turn with all the excited determinants that you can reach with your set of cluster amplitudes. So if you have chosen T1 and T2, the excited determinants that you can reach are singly and doubly excited determinants. So you will have to project with each of these in turn to get the terms in the equation for that cluster amplitude. Okay. Now, why is it called the equation for that cluster amplitude? That is because the expression that you get from projecting h bar with that excited determinant is used as the updating quantity for that cluster amplitude. I don't know if it's making sense. So because this is a nonlinear coupled equation, you cannot solve it in one go. So you have to take a guess, and then you have to find out the updates for each of your cluster amplitudes and feed them back into the equations. And then you keep doing this till your expression, which is basically chi h bar phi for the various, so chi h bar phi equal to 0. That is the equation you want to solve. Okay, but when you're using a guess t, then when you evaluate this, you will just get some value, not 0, right? So if this is chi ij to ab, for example, then the value that you get here is r ij to ab. So this is called the residue. Okay, and this residue must go to 0 as you solve the equation. And you use this residue to improve Tij to AB in the next iteration. Plus by some suitable denominator. Okay. So we don't need to go into the details of the denominator. So the denominator is, I can tell you in short, is the diagonal part of this matrix expression, for example. Okay. So if this is going to chi Lk to AB, then okay, let's not talk about it. It will take too much time. I want to talk a little bit about DFT. Anyway, so you have a suitable denominator which comes from the expression, and you use this quantity to update the cluster amplitude. So that is the iterative method of solving this set of nonlinear coupled equations. Okay, and once you keep doing this iteratively and your residues for all the cluster amplitudes, they reduce to 0, then you have the solution set of cluster amplitudes, and then you can go on to evaluate your energy expression. Okay. So ECC is equal to E0 plus, like I said, the expectation value of H bar with respect to what I was calling it phi Hartree-Fock. Okay. This is the Hartree-Fock energy plus this. So this is basically the correlation energy. So this is what you get eventually. So I did go a little quickly today. I'm sorry, but we don't have so much time. You can look at more examples, and they've worked it out more explicitly in the notes as well. So this is just to give you a flavor. And as you can see, there are a tremendous number of terms, so working them all out in class is just not possible. But you can sit, but the principle is the same, so you can sit with it and figure it out if you like. Okay. So this is about coupled cluster. Now I just wanted to talk a little bit about DFT. So, by the way, this is not part of your exam, so maybe I'll just start a new note. This is just Dft Basics. So far what we have done is we've always taken started with an expression for the wave function, and then we've used the Schrodinger equation. So one way is where you take approximations to the wave function is the first step in all the methods we've done so far. So for example, Hartree-Fock, CI, CC, MP2. Okay. So these are all called wave function based methods. So you try to guess what the wave function should look like. On the other hand, in DFT, you try to take approximations to the electron density. So what is the electron density? The electron density is basically a function of coordinate which tells you the number of electrons at each point in space in a atom or molecule. So this is basically a composite quantity for all the electrons. And if you remember the Coulomb operator from our Hartree-Fock theory, that could also be represented as a product of two densities. So a Coulomb operator, if you write it with the electron coordinates as 1 by r12, for example, that can also be written as an integral of the repulsion of two charge densities. So two net charge densities instead of talking about individual electrons. So what is the advantage of this? So the advantage of the charge density is that it is more amenable to classical models. So a charge density is something that you can imagine and you can model based on classical principles. While for the wave function, we only know certain principles, things like antisymmetry, them being an eigenfunction of spin, or we sort of impose some restrictions that the spatial paths should be the same for up and down electrons in the same at the same energy level. So those are the things that you ensure in a wave function based method. On the other hand, for things like density, you can take more physical models. Like a common one is an electron gas. So you can assume that the electrons in your molecule is like an electron gas, or you can imagine that they're like a charged liquid, or you can imagine that they are I don't know, that they decay with uh, decay as rho to the power minus 1/3 as you go to infinity. So you have more sort of classical pictures like that of the charge density, and that is what you try to impose on the density when you want to approximate it. Okay. But what makes DFT possible? So this is actually, if you think about it, guessing a form for the density that will fit all molecules is practically impossible. Okay, because the position of the nuclei in your molecule entirely determines how the electrons will move. So how are we handling this? So just a basic model. So if you say all molecules behave like an electron gas, that is just wrong. Okay. So you can say that maybe if there is only a central nucleus, then the rest can be approximated as an electron gas. Or if there is no nucleus, maybe then you can approximate the electron cloud as an electron gas. That would actually be pretty good if there is no nucleus. But when you have multiple nuclei, this is certainly not a good approximation. But there were two theorems, the Hohenberg-Kohn theorem, and there like two theorems by Hohenberg and Kohn, and then finally a procedure that was proposed by Kohn and Sham. So in DF, which were actually game changing. So the two most important things are the Hohenberg-Kohn theorem and the Kohn-Sham procedure. So what did the Hohenberg-Kohn theorem say? Before that, let's write just the Hamiltonian very simply. So I said no equations, but I think this doesn't classify as an equation. Okay. This is U. Okay. So I can write my Hamiltonian as sum of three terms: the kinetic energy of all the electrons, the electron nuclear attraction, and the electron-electron repulsion. Okay. So the T and U, they are universal in the sense that they do not depend upon the molecule that you're talking about or the atom you're talking about. Does not depend upon system. Okay. However, the electron nucleus attraction, that is called the external potential, and that is different from system to system. Okay. So what did Hohenberg and Cohn say? Hohenberg and Cohn said that the density or the ground state density and the external potential, they have a one-to-one correspondence. So what do they mean? They mean that if you know the density, the ground state density of a system, then you can automatically map back to the external potential applied on this system. Okay? And so let's think about it a little bit more. So if there are two systems of electron, one is trapped in a potential V1 and the other in a potential V2, and somehow you know that they have the same ground state energy, ground state density rho, then the two potentials can at most differ by a constant. So they are either the same or at most they differ by a constant. So this was theorem 1. So theorem 1 was that rho ground state determines V. So a density is unique to a potential, to put it very short. And the second thing was that if you evaluate the energy of a system given its ground state density, then this energy will be the minimum energy of the system. Okay. So if I can write the energy of a system as a functional of the density of the system, so if I can write something like this, okay, then if rho is equal to rho ground state, E rho is at its minimum. So this tells you how to determine the ground state energy in the first place. You have to write your energy as a functional of density, and then you have to minimize it with respect to the density, and this minimum point will be the ground state density, and you can feed it back to the functional to get the ground state energy. And also this rho ground state in principle tells you all properties of the system, just like the wave function can tell all properties of the system. Okay. And of course, given a wave function, you can always calculate the density. Given a density, of course, the wave function is not unique. So this is the thing. So this is about the Hohenberg-Kohn theorem. So Hohenberg-Kohn theorem is like an existence theorem. It gives you a recipe, but it does not tell you the procedure. So the breakthrough came when Kohn made some advances in how to use these Hohenberg-Kohn theorems. What did Kohn say? Kohn said that if I can have a non-interacting system with the same density as an interacting system, then I can solve the Schrödinger equation for the non-interacting system and obtain information about the interacting system. So this seems a bit too good to be true, right? That you can find a non-interacting system which will give you the same density as the interacting system. But actually this is not as weird as it seems. It can be done by constructing effective potentials from your interacting system. So just give me one more minute so that I can show you the Kohn system. Okay. So the Kohn system is basically like the Hartree-Fock system. Okay. The only difference is that instead of having a fixed, so in Hartree-Fock you have a fixed Fock operator for all the systems that you handle. It's the same Fock operator. Okay. And it has nothing to do, so the principle is that every electron moves in a field of the others, and that's it. So there is no tuning parameter involved there. On the other hand, for the Kohn system, you have something called the exchange correlation potential, which is a functional of rho again, and this is something that you guess empirically. So in trying to map your interacting system to a non-interacting system, you generate an effective operator which represents your interactions in the form of a one electron functional. So it's without going into equations, I think that is the best I can do. So you have an exchange correlation potential. So what does this have? What does this contain? This contains the effects of exchange. So if you have already constructed a density, or if you're guessing the density, you cannot build in the antisymmetry of the wave function into it. Okay? Why is that? Because the density has no property which reflects the antisymmetry of the wave function. But the antisymmetry contributes to the calculation of the, or it models the exchange interaction of the electrons, which is a real interaction. So how would you fit that into a density? You really cannot. You cannot. So if you have a potential which is a functional of density, your density cannot help. So you have to make a function of the density, which is the exchange correlation functional, which reflects this property. Okay. Also, this since you want to go over to a one electron picture, you cannot have a explicit correlation operator. So then again, you have to model that into a one electron picture. Okay, and all these interactions, which a one electron picture and a density representation cannot deal with, are clubbed into what is called the exchange correlation potential. And then you model this with empirical parameters, theoretical criteria, all kinds of things. And that's why you have a very large group of exchange correlation functionals, and some of them work for some systems, some for others, some are good for properties, some are good for energies. So it has become sort of like a whole bag of ingredients which you can use. But that allows us to do a lot of things in a simple way. So the idea of Kohn and Sham to club together all the complicated interactions into an effective exchange correlation potential and use this in an equation which is very much like the Hartree-Fock equation, that revolutionized the field of DFT, and then people could actually do a calculation. Okay. So the approach is quite different from the wave function based theories, and beyond the basic theory. So I only gave you a non-numerical overview, but of course there is a corresponding, you can have a more detailed exposition in terms of equations. But beyond that, when you go into the exchange correlation functionals, it's a forest. So that will take you quite some time. I have a note which is very nice. It's short, but it gives you all the flavors of the functionals. So I'll put it up on VLearn. That's only for those who are interested. It's not, so DFT is not part of your syllabus. So it's not going to be part of your end sem as well. It's just for your interest. Okay, so I will finish here today. I'm sorry, I just went a little bit over time. So if you all want to clarify doubts at some point, I think we can also have an extra class if you would like, and you have doubts. Okay. So whoever started the recording, please stop it, and then we'll finish here today.
Okay, thank you, ma'am.
Yeah, thank you.